Hi everyone, welcome back. And today in lecture 3.8, we are going to complete our work in the carboxylic acid derivatives chapter 21. So we will do the second half of that chapter, 21-4 through 21-7. Basically what we're going to go through is, now that we've seen the nucleophilic acyl substitution reaction and mechanism and looked at it in the context of a carboxylic acid, we will then look at it in the context of the different types of carboxylic acid derivatives. And we'll start with the most reactive acid halides, and we'll work our way down to the least reactive amides in order of their reactivity. So just overview of what we're going to do. I'm going to be going through, you'll see in the beginning, because of the more reactive nature of acid halides, there are a lot more reactions that are available from them. As we go down the list, we will see repeat reactions, and we will also see less reactions. So most of the information is up front, and then there'll be a few little, for each one of these sections, we'll go into a few details that are specific and important for those functional groups that are unique to them. So that's what we're going to be going through. Let's get started with the chemistry of acid halides. So as we know, the functional group acid halide is a carboxylic acid derivative in which the acyl group is bonded to a halogen. And that halogen for acid halides is almost always a chlorine, occasionally is a bromine, and we don't see any of the other halogen atoms in normal, other than the much more exotic realms of chemistry. So acid halides are either acid chlorides or acid bromides, and we can prepare them from their carboxylic acids. Now, carboxylic acids themselves are not nearly as reactive as acid halides. So, because of the leaving group properties and the resonance through the carbonyl system. So, to prepare an acid halide, as we've seen, we have to convert the carboxylic acid into something much more reactive so that a chloride can displace that leaving group. And what we use to make acid chlorides is thionyl chloride. Similarly, we can make an acid bromide by using phosphorus tribromide, or PBr3. So these are the two methods available to us to make acid chlorides and acid bromides out of carboxylic acids. Now let's talk about the reactions of acid halides. And as I go through this, realize that the reactions are essentially the same for if you use the acid chloride or the acid bromide, with the acid bromide being slightly less commonly used because it is a lot more reactive because of the bromine atom being a better leaving group than the chloride. So the acid chloride is typically the one we use in the examples, and that's the one I'll show, but these reactions also work with the bromide. So we'll start with hydrolysis, which is the reaction of the acid chloride or the acid bromide with water. And when an acid chloride or an acid bromide undergoes hydrolysis, it's converted, like all of the carboxylic acid derivatives, into a carboxylic acid. So if you take any carboxylic acid derivative and make it undergo hydrolysis, it will turn into a carboxylic acid. And that's exactly what happens with an acid chloride. The water acts as a nucleophile and performs the nucleophilic acyl substitution, displacing the chloride, and then leaving behind a carboxylic acid. Notice that an equivalent of hydrochloric acid is produced during the course of the reaction. For this reason, the reaction is often done under basic conditions in order to neutralize the hydrochloric acid as it's formed for a variety of reasons, one of which is to minimize any interference with other functional groups that might be present. Another reason is to sequester the HCl so that it doesn't go off into like the fumid and cause corrosion. And there are other reasons as well, but those are some of the main ones. And the base that's often used for this is pyridine, which we abbreviate PYR. Now, seeing as though to make an acid chloride, you would start with a carboxylic acid, right? We take a carboxylic acid, we convert it to an acid chloride using thionyl chloride. Why would we want to turn it back into a carboxylic acid by treating with water? Isn't that just kind of defeating the purpose of the acid chloride in the first place? And I would say probably, yeah. I mean, I can't think of a lot of examples. I'm sure some exist for doing this reaction, the hydrolysis of an acid chloride. I just can't think of any practical reason at the moment for doing that. One thing that this is important to note, though, is the hydrolysis is how someone handling acid chloride would handle it, is that they would keep it away from water to prevent this from decomposing it. So I look at this as more of a decomposition reaction than a practical thing. So it's more of a warning, like, hey, be careful if you put this into water. And if you do put it into water, you're going to get a bunch of HCl. So storage of acid chlorides is typically done in a way that minimizes any possible interaction with water. So we parafilm the cap, we store the thing in a dry fridge or in a desiccator while we have it out. And then when you go in and out of the bottle, you're using dry glassware, that kind of stuff. And then you always dry your glassware before you use an acid chloride, because it will decompose into a carboxylic acid. So that's hydrolysis. Let's look at the next reaction, which is a little more practical. We can take an acid chloride and convert it into an acid anhydride. So as we saw in the previous lecture video, making an anhydride at an industrial scale is usually done to prepare acetic anhydride, where they take acetic acid and they heat it up to like 800 degrees Celsius, and then it removes water, and then you can prepare this acetic anhydride. Now that's limited to acetic anhydride. If we wanted to make more complicated anhydrides or mixed anhydrides where we don't have both sides that are the same, the best way of doing that is to use this method, which is to convert an acid chloride into an acid anhydride using a carboxylate. So here's what the overall reaction looks like. So to prepare this anhydride from an acid chloride, we of course start with the acid chloride. Typically in ether is dissolved, and to that is added the sodium salt of a carboxylate. A good question to ask would be, well, where would you get a sodium carboxylate? Well, we would prepare the sodium carboxylate from the carboxylic acid by treating it with sodium hydroxide. Now, a lot of times this is something where you can buy the sodium carboxylate that you want, and it's prepared that way. But if you needed to prepare one, probably the easiest way to do it would be to prepare it in something more volatile than water, but that's still polar, so like an alcohol, because you want to evaporate that alcohol afterwards. So probably if I was doing it, I would use something like maybe, I guess, ethanol or potentially methanol, and I would dissolve the carboxylic acid in methanol, and then I would add sodium hydroxide in an equal molar ratio, kind of like a titration. And at some stage, I would complete the deprotonation of the carboxylic acid. Then I would evaporate all of the aqueous material and all of the alcohol material, and then I would have my sodium carboxylate that I could use in this reaction if I needed to make one. And that gives you a lot of power, so you can make any kind of anhydride that you need. Here's an example reaction. So the example I'm drawing here will be a mixed anhydride. And what I want us to do is to show two different routes to the same mixed anhydride. So we're going to need to use in each route, a different acid chloride. So I'm going to start by imagining the first way to make this anhydride would be using the acid chloride on the left-hand side. So I'd be disconnecting this bond between the oxygen and the acyl carbonyl carbon. So if I did that, I would use the acetyl chloride, or the CH3 carbonyl chloride. That's called acetyl chloride. And then my carboxylate salt would be this part. So as I'm drawing this carboxylate, let's also think about what other conditions we might need for this reaction. Do we need to use base? Well, to answer that question, think about this. Do we have a proton on our carboxylic acid to make HCl gas? Well, no, because we're using a carboxylate. The reason why HCl gas was produced in the hydrolysis of acid chlorides is because water was the nucleophile, and water has protons on it. The proton will make the H on the HCl. So we don't have that case here, so we don't need to use any base. The only conditions that we would kind of think about would be our solvent and our temperature. And that's usually something like ether or THF at room temperature. So now let's do the other half. Or the other way of doing this by looking at the other half of the molecule. Well, on this other alternate synthesis, we would be disconnecting this bond instead. So our acyl chloride is a different part of the molecule. It would be this. And then if that's our acyl chloride, then we'd use the sodium salt of acetate. So sodium acetate for the nucleophile. And same thing, ether, room temperature. All right, so now that we have the hydrolysis and the conversion to acid anhydrides down, let's turn the page and see what other reactions we have available for the acid chlorides. Now, similar to their reactivity with water, acid chlorides also react with alcohols. The difference being that we have an R group instead of an H like we do on water. So we have alcohols, just like water, act as a nucleophile on that acid chloride. This is called alcoholysis, and the overall reaction is we take an acid chloride plus an alcohol, and it makes an ester. That's called alcoholysis. Now notice that we have a protic nucleophile, our alcohol. So that means that we will also produce hydrochloric acid during the course of this reaction. So this formation of hydrochloric acid during the course of the reaction has some important implications for this ester that we want to make theoretically in this reaction. One of the problems is that under acidic conditions with, say, water around or other nucleophiles, this ester could be decomposed by hydrochloric acid. There's an acid-catalyzed hydrolysis reaction of esters. So if there's water around, or even if there isn't, it will slow the reaction down because of the reversibility and the decomposition of the ester. So it's important in these reactions to sequester that HCl as it's formed, and for that reason we always use pyridine or triethylamine or some other base, an amine base in the presence of this reaction. So let's take a look at a few examples. I'll start us off with a pretty straightforward reaction where we're going to take acetyl chloride and treat it with an alcohol. How about isopropanol? And I'll make sure to write down pyridine as the base. And let's see if we can draw the product for this. So the isopropanol is going to act as a nucleophile on that acetyl chloride, do the nucleophilic acyl substitution, and we should generate this ester, which is called isopropyl acetate. So let's try another one. And in this example, I want to show how the reaction can work in an intramolecular fashion. So I'm going to draw carboxylic acid and an alcohol on the same ring, on this benzene ring. And let's see if we can imagine a way to convert this using our acid chloride into this four-membered lactone ring that I'm drawing here. Remember, a lactone is a cyclic ester. So how can we convert this, like carboxylic acid alcohol, into this cyclic ester? Well, if we treated it with thionyl chloride in the first step, that would convert the carboxylic acid into an acid chloride. And then the nucleophile would the alcohol, that nucleophilic OH, would spontaneously cyclize with that and displace the chloride in a nucleophilic acyl substitution reaction. And that would give us our lactone. All right, so the next reaction looks like aminolysis. So let's scroll down and talk about that. So aminolysis, again, is the reaction of an amine with, in this case, our acid chloride, but any of the carboxylic acid derivatives. So let's look at the general reaction. We have an acid chloride, and we treat it with an amine, and what we get after the nucleophilic acyl substitution is an amide. Now let's talk about the conditions, and first let's see if we need to worry about HCl formation. So notice that our nucleophile does have a proton on it. It's a protic nucleophile. And that proton, along with the chloride that's on the acid chloride, neither of those atoms are present in the amide. And that's because they form HCl. So that HCl does need to be sequestered in this reaction. So the way this is usually done is instead of adding pyridine or some other external amine, just additional amine of this, like for example, in this case, we would add 2 equivalents of this stuff so that it reacts with the hydrochloric acid instead of adding extra amine. So those are the most important conditions. Solvents vary a lot with these. So it's important that you use a dry solvent because of the acid chloride. And, it depends a lot on the structure of the amine because amines have very differing solubilities. Sometimes they're not very soluble in organics. Sometimes they are. It really depends a lot. So we probably won't talk about the solvent too much on it. Beyond that, it's a pretty straightforward reaction. Let's look at a few examples to see the variety that you can get out of the different amides. So I'm drawing here a famous carboxylic acid known as lysergic acid, and it's in a class of compounds known as ergot alkaloids. And it turns out you can take this ergot alkaloid called lysergic acid, and it can be transformed into an amide that I'm substituting the large ring system here with an R group. It can be turned into an amide with 2 ethyl groups on the nitrogen. It's called the diethylamide. And that's another famous molecule known as lysergic acid diethylamide, or LSD. So apparently this is, I think, the last step in that preparation. Once you have the lysergic acid, it's converted into this amide. What conditions would we use to do this? Well, we have the carboxylic acid. We need to make it into an amide, and we can't go directly from the carboxylic acid to the amide. We have to go through that acid chloride because the chloride is much more reactive than the carboxylic acid. So we need to convert that carboxylic acid into an acid chloride. So step 1 would be thionyl chloride. And then in step 2, we would treat it with diethylamine, and that would give us our diethylamide. So it's an important thing to think about if we want to make a disubstituted amide where there are 2 R groups on the nitrogen, we use an amine with 2 R groups on it. If we wanted to make an amide with 1 R group on it, we would use an amine with 1 R group. And that's what we're limited to. We can't actually use amines with 3 R groups on them because that makes a quaternary ammonium salt, which isn't going to be stable. So we're limited to primary and secondary amines for this. So let's go to the next reaction of acid chlorides, which is their reduction. So while acid chlorides aren't typically reduced because normally the more readily available compounds such as an ester or I guess theoretically a carboxylic acid could be reduced easier to an alcohol than an acid chloride, nonetheless it can still be done. So for example, you can use lithium aluminum hydride and reduce the acid chloride in ether to a primary alcohol. And this involves an aqueous workup afterwards to isolate the alcohol. Here's an example reaction. So as you can see, the acyl carbon, or the carbonyl carbon, is reduced to the alcohol oxidation state. And that involves delivery of that hydride from lithium aluminum hydride to that carbonyl center, performing a nucleophilic acyl substitution. That gives an aldehyde intermediate, and that aldehyde is subsequently quickly reduced, and that's where we get the alcohol from. And it's very difficult to imagine stopping the aldehyde from being reduced, although you'll see in the book, I think in this part, it mentions a reagent known as DIBA, or Dibol H, that allows you to make aldehydes if you use these very specific conditions. And it's a kind of an unreliable reaction. You should be aware of it. I don't typically instruct on it though, because frankly it doesn't work very well. So anyway, that's that. Let's go to the next page. All right, so now we are going to look at a few reactions of organometallics with acid chlorides. So we'll look at Grignard reactions and Gilman reagents, which are both very useful reactions with acid chlorides. It allows us to make ketones, it allows us to make interesting alcohols. So let's see how all of this works. So first, let's take a look at the reaction of a Grignard reagent with an acid chloride. So the reaction overview is this. We have an acid chloride, and we treat it with a Grignard reagent, so RMgBr in diethyl ether. That's all in the first step. And then in the second step, we do an aqueous workup with acid to hydrolyze the Grignard salt. And then what you would find in the end is that you would get a tertiary alcohol. Now, this is interesting. We have two R groups, those R primes, that come from the Grignard reagent. So that Grignard reagent, we need to provide two equivalents of it because it needs to put on those two R prime groups. So we get a tertiary alcohol. Let's look at the mechanism for how this works. Why do we get two R primes? So the Grignard reaction with the acid chloride starts with a nucleophilic attack by that R group onto the carbonyl carbon. And that breaks the pi bond, and we form the tetrahedral intermediate. And that tetrahedral intermediate, notice, has an R prime on it. That came from the Grignard, so there's R1 equivalent. Notice also, though, we have the chloride leaving group. And what always happens to tetrahedral intermediates? Well, they always collapse to kick off a leaving group, and that's what happens in the next step. The pi bond reforms, and the chloride gets kicked out. So what is the result when that tetrahedral intermediate collapses and kicks off the chloride? The result is a ketone. So we have a ketone with an R and an R prime, and we have two equivalents of the Grignard reagent. So there's another R prime that is a negative charge around that nucleophilic R prime. That's going to attack the carbonyl carbon, break the pi bond, and form another tetrahedral intermediate. Now, this tetrahedral intermediate salt that we have does not have a leaving group, so it can't collapse and kick off an R group. So it's kind of stopped at this point. This is when we work the reaction up with acid and water to get the tertiary alcohol. So if we take a look at it, where did the two R primes come from? Well, they came from successive additions onto a carbonyl carbon each time that it formed. The first time was the collapse of the tetrahedral intermediate to kick off the chloride, and then attack on that ketone led to the tertiary alcohol. You might ask the question, well, what if I only used one equivalent of the Grignard reagent? Would I be able to stop at the ketone? And the answer to that is no, not with the Grignard reaction. The reason why is that you have a lot of Grignard around. So the molecule doesn't know you only put one equivalent. The molecules don't know there's only one equivalent. At the minute a ketone is formed, it reacts with the Grignard reagent. So you end up with some tertiary alcohol. But you've just consumed some of the Grignard reagent that was necessary to react with the acid chloride. So in the end, you end up with a mixture of acid chloride that gets turned into a carboxylic acid after the workup. You end up with some ketone and you end up with tertiary alcohol. So you get a really nasty mixture. So you actually, if you don't provide the two equivalents, you get nasty mess. But if you do, you get nice clean conversion to the tertiary alcohol. Now, there is a way to actually stop and get a ketone using an organometallic reagent. And that would be the Gilman conditions, the Gilman reagent. So let's take a look at how that works. So you might recall that a Gilman reagent is also known as a lithium dialkyl cuprate. So it looks like this. We have a copper metal center with two alkyl groups on it. And this entire construct, this copper with two alkyls, has a negative charge, and it's counterbalanced with a lithium cation. So it's called a lithium dialkyl cuprate, or a Gilman reagent. And what this does is it provides one of these R groups, which are always identical with one another, as a R minus, like the Grignard reagent does, except that it changes the chemistry a little bit because of the copper and its size compared to, and the electron cloud of it compared to magnesium makes it what we call a softer nucleophile. And it doesn't, this softer nucleophile doesn't react like the Grignard reagent does so quickly with the intermediates. And what it allows you to do is to take an acid chloride, react it with a Gilman reagent, and isolate a ketone. So how exactly and why exactly does this work this way with that copper? Well, let's take a look at a proposed mechanism. So we have our acid chloride, we have this Gilman reagent, which is the copper bonded to the R groups, the R primes, and that's negative. And that copper has this large electron cloud. It acts as a nucleophile, interestingly enough. That does the nucleophilic acyl substitution on the acid chloride, and that produces an acyl copper intermediate. And this is where it delivers very closely, almost in an intramolecular way, that R prime to the acyl group, right? And then the copper gets reduced and kicked off. And that's where we get this ketone from. And the reason why this can work and with the magnesium it doesn't is that the magnesium, with the Grignard reagent, that is not an intramolecular reaction. The Grignard is external to the carbonyl when it delivers those R groups. In this case, the acyl is stabilized by the copper's electron cloud, so it doesn't react with anything other than that R prime that's close to it. And then that ketone further, it can't react with the copper species anymore, so it's done at that stage. So this is why this reaction works. It's a nice way to make the ketones. The only trouble is that it's very difficult often to make the Gilman reagents because they're very, very sensitive to oxygen and in the air and water. Also, you lose one of the R primes that you build into that Gilman reagent. It is useless. So if it's something that's complicated, that would be a very expensive thing to throw 50% of away. So let's just do an example reaction for each of these, the Grignard and the Gilman, to see it in a practical way. So let's start with a Grignard example. So let's use this benzyl chloride and treat it with the methyl magnesium bromide in diethyl ether. And second step, we will treat it with the aqueous acid workup. So what product should we get from this? Well, we're going to add that methyl group, two equivalents of it, onto that carbonyl carbon. So we should get two methyl groups and a tertiary alcohol with a benzene ring on the other side, like this. Now let's compare this product with what we would get if we used the same acid chloride and a similar Gilman reagent. So my Gilman reagent should have two methyl groups attached to the copper metal center, and then a lithium counterion. That gives me the lithium dialkyl cuprate that we call the Gilman reagent. And we're going to attach one of those methyl groups onto the carbonyl carbon, displacing the chloride to get us a methyl benzyl ketone, like this. So that is a list, pretty complete list of the reactions that are interesting with acid chlorides. So now we're gonna change to the next category of carboxylic acid derivatives, the acid anhydrides. That's on the next page. Okay, so now we're going to talk about acid anhydrides, also just usually said anhydrides. Acid anhydrides have pretty similar reactivities as acid chlorides do. They're a little bit slower to react, and they're a little more stable to things like the environment. So it's like you don't have to be quite as cautious with them. They're relatively stable compared to acid chlorides. Their preparation we've already learned about in the previous section. We just went over that. Take an acid chloride, carboxylate salt, make an acid anhydride. So we don't need to see that again. Let's go into the reactions, and basically because they're less reactive than acid chlorides, the only real common reactions that people do with them are alcolysis and aminolysis. So let's look at those two. So alcolysis and an acid anhydride, the reaction looks like this. We take an anhydride, we treat it with an alcohol, and just like you would expect with an acid chloride, we get an ester. So it's really the same thing, it's just a different leaving group. So it turns out because of its more mild properties and less interference with certain other functional groups, as well as its ease in handling and relative ease in workup, people use acetic anhydride. That's the most common, by the way, anhydride is acetic anhydride, to do a lot of different transformations into acetate esters. So, for example, aspirin is prepared from salicylic acid by the acetylation of salicylic acid using acetic anhydride. That's one of the most common uses for it, actually. So we can take acetic anhydride and make these acetate esters with an alcohol. So that's an example of how acetic anhydride is used to acetylate salicylic acid in making aspirin by protecting, or you can think of, or hiding that hydroxyl group as an ester instead of a hydroxyl group. The reason why that's done actually is that salicylic acid hydroxyl group is a very acidic proton on it, and it causes a lot of problems in the gastrointestinal tract. And so when that's masked as an acetate ester, it no longer has that property, or it has less of it. And it also metabolizes in a slightly different way. So it's better. And that's why we use aspirin instead of salicylic acid. And this brings up an interesting concept, though, is the acetate ester is used very frequently as a protecting group for alcohols. It's a way of masking or hiding an alcohol, particularly in the world of carbohydrate chemistry and peptide chemistry. And I was going to show you an example of taking glucose, which is a very common thing to do if you're in carbohydrate chemistry, is to protect something like glucose or another monosaccharide as all of the hydroxyl groups on it as acetate esters, and it's usually done using acetic anhydride like this. So each one of those hydroxyl groups on glucose is now turned into an ester, an acetate ester, and this completely changes the properties of the glucose. Normally glucose is soluble in water, quite soluble in water. This acetate glucose is not soluble in water, or very sparingly soluble in water. And then different reactions might take place where you remove one of them, and then you do chemistry on that part. And then later on, you might deprotect or remove all those acetate esters. We'll learn actually how you remove an ester is under saponification conditions, which is sodium hydroxide. We'll learn that when we learn about the chemistry of esters. So let's go to the next part now, and let's talk about cyclic anhydrides, which are different than the ones we've been looking at. We're looking at sort of open chain anhydrides. There are also cyclic ones, and they're kind of interesting. So let's scroll down and take a look at that. So it's really common to see cyclic anhydrides like succinic anhydride, which I'm drawing here, and phthalic anhydride, which I will also draw after succinic anhydride. And these cyclic anhydrides act in the same types of reactions that we see with regular ones, except that the leaving group is tethered to the molecule. So let's see if we can predict what would happen if we took succinic anhydride and we treated it with ethanol. What product would we get? So the first thing we have to expect is the nucleophilic addition onto that succinic anhydride carbonyl carbon. That breaks the pi bond to the oxygen, and we form a tetrahedral intermediate with that ethanol attached to the carbonyl carbon. And that's protonated, but so the pi bond reforms and kicks off that carboxylate leaving group. So now what we have is a carboxylate and a protonated ethyl ester on the same molecule. So we get a proton transfer, which gets rid of the charges. So we have a carboxylic acid and an ethyl ester. So that's what we would form from this succinic anhydride addition of ethanol. You might try a similar exercise with phthalic anhydride and see if you can draw that product. There's also an exercise in the book in this section with phthalic anhydride that you can give it a shot. So those are the reactions that we need to be aware of for anhydrides. Let's go and talk about the chemistry of esters. Well, I was wrong. We're not in esters yet. We still have to talk about aminolysis and anhydrides. So let's do that. So if we take an anhydride just like an acid chloride and we treat it with an amine, it goes through aminolysis and this produces amides. And this is definitely a reliable and effective way to make amides. So I'm not going to go through all the details. It's exactly the same as acid chlorides. So I'll show you this general reaction, and then let's move on to esters. So preparation of esters, we previously learned one great way of making them is from carboxylic acids using the Fischer esterification. In the Fischer esterification, we start with a carboxylic acid, and we boil it in the alcohol that we want to attach to that oxo in acid and obviously with heat because we're boiling it. And then that will produce the ester usually in great yields. There are some limitations because of the availability of complex alcohols or the carboxylic acid component, but this is definitely a reliable and effective way of making esters. We can also use the SN2 reaction between a carboxylate and a primary or secondary alkyl halide to make an ester. And a third method for preparing esters starts with acid chlorides. If we take an acid chloride and we treat it with an alcohol, in the presence of pyridine, it will produce an ester in high yield. Now we need to make sure we use the pyridine to sequester the excess HCl that's generated during the course of the reaction. Otherwise, this can be reversed or stalled out. So what we isolate is the ester and the hydrochloride salt of pyridine in the end. So those are the three major methods for preparing esters, from carboxylic acids, from carboxylates, or from acid chlorides. So let's talk about the reactions of esters, and we will start off with hydrolysis of esters. Now, esters can be hydrolyzed, split with water, reacted with water, under acidic or basic conditions, and like all carboxylic acid derivatives, they will hydrolyze into carboxylic acids. Under acidic conditions, actually, they produce a carboxylic acid in its protonated form. But under basic conditions, also known as saponification, hydrolysis yields a carboxylate salt because you're under basic conditions. So here are the reactions for those. So under acidic conditions, the hydrolysis of the ester gives the carboxylic acid. But under basic conditions, which we also call saponification, we get the carboxylate salt. And the metal counter ion is from whatever metal was in the base. So it could have been sodium hydroxide, potassium hydroxide, or whatever that metal happened to be. That would be the counter ion on that salt. And this carboxylate is under basic conditions. Again, that's called saponification. Now, this hydrolysis of esters is actually, I think, the first step in the metabolism of triglycerides, which are fats. The enzymes in the liver hydrolyze this, a triglyceride, which is an ester, into the carboxylates. So let's actually, I think it's a good idea to look at the mechanism of it. I'm going to look at both the acid and the base catalyzed mechanisms. And then I'll show you also just what a triglyceride looks like right after that. So let's take a look at the mechanism. So the mechanism starts off by activating the ester carbonyl oxygen through a Bronsted proton transfer. So now we have this oxonium oxygen, so that's an activated ester. It's more susceptible to nucleophilic attack. The water nucleophile attacks the carbonyl carbon, breaking the pi bond to form a tetrahedral intermediate. So this tetrahedral intermediate has that protonated oxygen. That proton gets transferred to the leaving group, which productively in this case will be the alcohol component, the OR. That gets protonated. If it does, that would be a good leaving group. And for the mechanism to proceed, that needs to be the leaving group. So now we push down the electrons from the oxygen to reform the carbonyl, kicking off that alcohol leaving group, and we essentially have our carboxylic acid. It's still protonated. We also produce the alcohol. And that protonated oxygen, we just lose the proton to the acid catalyst that we're regenerating, and we're left with our carboxylic acid and the alcohol. So that's the mechanism for the acid catalyzed hydrolysis. Let's now do the base catalyzed hydrolysis mechanism. So just like in the acid catalyzed mechanism, we're taking an ester and we're hydrolyzing it. But under basic conditions, we have hydroxide, which is a great nucleophile. We don't actually need to activate the carbonyl. So we get direct nucleophilic addition to that carbonyl carbon. And now we have a tetrahedral intermediate that is a negative charge. It's not positively charged, it's negative because we're under basic conditions. Now we kick off a leaving group by regenerating that carbonyl carbon, and the leaving group is the alkoxide, or the hydroxide, but that would go backwards. If we lose the alkoxide, that's a productive step that leads towards the carboxylate. But first we have this carboxylic acid that's formed. And this is where that alkoxide will jump in and deprotonate, and that leaves us with the carboxylate salt and the alcohol. And this method, this process, I should say, is known as saponification. And it's how soaps are made. It's also how a lot of, in our bodies, we naturally, we use acidic conditions, so we don't saponify. But this is how triglycerides are broken down into things that we use for soap. So what is a triglyceride? Let me draw a structure for a triglyceride for you. So the first molecule I'm actually going to draw is not a triglyceride, but is in fact an alcohol called glycerol. And glycerol, as you can see, has 3 carbons and a hydroxide at each carbon. It's very good at hydrogen bonding, it's very viscous. And actually, a triglyceride is based on this alcohol, where there is a carboxylic acid that has formed an ester at each of these alcohols. So if we imagine having an ester at each OH group, that is what a triglyceride is, as I've drawn here. So in fats, like in animal fats, plant fats, the fats are stored as triglycerides, where the fatty acid chains are attached to this glycerol. And when soap making happens, you get a bunch of like olive oil or some other fat. You do saponification, and it releases those fatty acid chains as carboxylate salts, which are soluble in water because they're now salts. Previously, as the triglyceride, they're not soluble in water, so they wouldn't work as a soap. They're an oil. But once you saponify them, they become salt-like, and then they also clean fat off your hand. So it does both things because of that polar-nonpolar thing going on. Also, natural soaps have a component of glycerol in them, which is like a kind of like a lotion in a way. So that's saponification. Let's go to the next page and see what's happening there. So continuing and wrapping up our discussion of esters, we're going to talk about reduction in Grignard reagents with esters. Aminolysis is not used with esters to make to make amides. It's not a practical reaction. It's just easier to start with an acid chloride. So we're not going to go over that one. Reduction, though, is something that you can definitely do with esters. We can treat an ester with lithium aluminum hydride, and from that we would form a primary alcohol. The book goes into another way that you can take an ester and reduce it selectively using dibol H or dibol H, and that is something, if you're curious about it, feel free. It's an interesting reaction. I'm not going to really focus on it too much in here. Let's focus on this lithium aluminum hydride reduction. So we've already learned about that. I'm not going to go into more detail. Let's go down and look at the reaction of esters with Grignard reagents. So just like with acid chlorides, esters react with Grignard reagents to form tertiary alcohols by the same mechanism. So we need our ester, and we need 2 equivalents of the Grignard reagent and an aqueous acidic workup, and then we see 2 of the R groups from our Grignard reagent get added into that carbonyl. So as we've already seen a few examples of this type of reaction already, I want to give you one that's not like just as simple as the previous examples. So let's start with a lactone as our ester. Now, again, lactone it's just an ester, but it happens to be in a ring. But it still reacts just like a regular ester. And so it should behave the same way in a Grignard reaction. Now let's use our Grignard reagent. We'll use the phenyl magnesium bromide just to change it up a little bit. So this has a phenyl group, which is like a benzene ring, as the R. Now what I want you to do is figure out what would be the product after the aqueous workup. See if you can draw it. So the first thing we should do is just analyze this lactone, and I'm going to put little red dots around and number the carbon atoms in the ring. So there are 5 carbon atoms, but there's also an oxygen atom in the ring. So it's 1 through 5, but there's also that 6 atom there. So I'm going to draw a chain for the product since we're opening the chain through a nucleophilic addition. And we'll have the 5 carbon atoms. At number 1, we're going to have the hydroxyl group from the alcohol and the 2 phenyl groups that we're adding in as nucleophiles when we open up that ring. When we open up that ring, the leaving group is the hydroxide at carbon 5, so it's atom 6. That's the leaving group for it. So basically each phenyl group attacks that carbonyl at 1, and that generates, the first one generates a ketone, and then the second one generates the alcohol, and then we kick off that 6. So that's the product. I hope you got it right. Let's go to the next page. So now we are in the last of the carboxylic acid derivative categories, which is amides. So we are going to discuss briefly the chemistry of amides, their preparation. As you've learned, amides are readily prepared from the more reactive carboxylic acid derivatives. Mainly acid chlorides are probably the best way to make them. We take an acid chloride, we react it with an amine, and that produces an amide. So if you wanted to look at that reaction up, go back to the acid chloride section. So now we can talk about the reactions of amides. And just in general, amides are very stable. They're the most stable of the carboxylic acid derivatives. So there aren't as many laboratory, like in the synthesis realm that we do. Usually amides are it's the end of the road for chemistry. Like you don't take amides and try to go uphill from them because they're very stable because of the nitrogen resonance and other aspects of it. However, reactions of amides are very important. For instance, when we eat protein, our enzymes, called protease enzymes, have to degrade those proteins. And proteins are composed of a bunch of amide bonds. And so that's kind of an interesting thing, and it's actually the hydrolysis/alcoholysis of an amide. And this diagram, I decided we would just leave it here. It's enzyme promoted, so I thought we would just show it from the book. It follows the same principles, though, that we've seen for our non-enzyme catalyzed reactions. So you can see here in the first step of the mechanism, what's going on is a base is coming in and deprotonating the enzyme, making the enzyme oxide, so that that's a nucleophile, which then attacks the carbonyl of the protein. So it's after that nucleophilic addition by that enzyme that the tetrahedral intermediate is formed. And now this tetrahedral intermediate is attached to an enzyme substrate. So all of the reactions that can happen are now catalyzed by that enzyme and the local area around it. And what happens at the tetrahedral intermediate stage here is the same that happens in the mechanisms we've seen. It collapses and we lose the leaving group. Now the leaving group in an amide is this amine, like right in acid chlorides it was a chloride, in esters it was an alcohol, in hydride it was a carboxylate. And now here we are with amides and it's an amine. So that amine is kicked off, and what we're left with is this acyl enzyme substrate that then undergoes further hydrolysis that cleaves off that end carbonyl stage. And this is where we get another tetrahedral intermediate, which falls off, and then we get an acyl cleaved protein fragment. And the enzyme gets back, the catalyst is regenerated. And this is a protease's action, how it takes apart a protein. And proteases are used in our, I don't profess to know a lot about it, but proteases, I know a little bit about it, is they degrade proteins. And that's a part of metabolism. It's also a part of other physiological processes, very important stuff. But this is, I wanted to show you, like if you go into biochemistry, these are the mechanisms. It's the same as the mechanisms that we are using. Now let's move on past the hydrolysis or alcoholysis and talk about reduction. Now this is one of the useful reactions of amides. Now amides, they're very stable. So like, we're not going to be turning them into acid chlorides. But what's cool about amides is you can reduce them to primary amines. And we can do that using lithium aluminum hydride, just like we would do with nitriles, actually. It's almost the exact same thing. So if we take an amide and we treat it with lithium aluminum hydride, we can produce a primary amine. So let's look at an example of this. I'm going to draw a molecule that has two functional groups that we can reduce. So I'll include both an amide over here, and then over on the other part of the molecule, I'm going to draw a nitrile. So we can reduce both of those with lithium aluminum hydride, and we would expect both to reduce to a primary amine. So here's the structure of the primary amine we would expect. So now that we've learned about that, let's look at the analogous structure for an amide that an ester, we had a cyclic, remember we had a cyclic ester, we called it a lactone. There's an analogous structure for amides, and they're called lactams. So let's turn the page. There's a few example reactions with lactams. So let's talk about what lactams are first. So I'm going to make a comparison to just regular amides. So we know the amide functional group. We've got this nitrogen attached to a carbonyl. It has 3 bonds. Now, a lactam is a cyclic version of this. So we have the same basic functional group, except that the nitrogen is tethered to the R group in a cycle, in a ring. And this is called a lactam. And lactams happen to be very, very important in for instance, in medicine. Antibiotics are famously what are called beta-lactams, which are 4-membered ring lactams. Lactams are also highly prevalent in a lot of other biological processes and natural products. So it turns out lactams are also undergo similar reactions, sometimes a lot more reactive than regular amides because of ring strain, if they are small rings like beta-lactams. So one reaction that lactams can undergo is reduction with lithium aluminum hydride to make an amine. So let's take a look at how that would work with, say, a regular, like a 6-membered ring lactam. So when we're drawing the structure of the product, we just want to make sure we have an amine, and we're not opening the ring or anything. So we're just going to have that nitrogen as now a secondary amine because it's in a ring. So that's how the reduction of lactams, what the types of products we would see. Let's look at a synthesis problem that ties a couple of these reactions together. So let's take a look at this example. I took this from the book. As you can probably see, I cut and pasted it. So we've got this cyclobromine, and we need to turn it into this amine. But there's a carbon between the nitrogen, which has 2 methyl groups on it, and that ring. So we need to devise a route to make the carbon-carbon bond and also make an amine at the same time. So take a moment and work through a couple of these and try to write down all of the steps that you can come up with, and I'll show you my solution. So I'm actually going to work backwards from the product to show you how I imagine it. So this is an amine, and I know I can get that by reduction of an amide using lithium aluminum hydride. So I just replace that functional group amine with the appropriate amide with the right number of carbon atoms in it, and then use LAH to do the reaction. Now this amide, I have to figure out where did that come from. Well, I know amides are made from like acid chlorides and amines. So if I disconnected the bond between that carbonyl carbon and the nitrogen, and imagine it coming from an acid chloride with the 6-membered ring and dimethylamine, and I would need to use 2 equivalents of that dimethylamine, I mean, because I need to sequester all the HCl that's being produced. So I use 2 equivalents of the amine. And then I need to imagine where did that acid chloride come from? Well, I can make those from carboxylic acids and SOCl2. And then how do I make this carboxylic acid? Probably the trickiest part. I do a Grignard reaction from that alkyl bromide and CO2, or dry ice, to carboxylate it. So this is a good problem. It ties together a lot of the reactions from each of the functional groups that we've learned. I think you should try to find more of those in the book. There are plenty of them to practice. It's a good idea to see how all of these pieces fit together into a bigger picture. It also shows you the power of these reactions to get from one thing that's very different into a completely different thing through all of the different functional group interconversions, as well as the carbon bond forming reactions. So that's going to wrap this lecture up. Let me know if you have any questions. I hope you're doing well.